the simulation. Okay, so therefore I'm going to just open up my simulation. Open. This one is assignment 3. So assignment 3, the diode. So figure 1 and figure 2. So I'm going to look at figure number 1. Okay, so this is a figure number 1. Let me go ahead and zoom it up a little bit. So you want to do is turn on your simulation. So we're going to do DC. So first one, they said they want to measure what point B. So therefore you want to put the high at point B and the low at common. Okay, and then you turn on your simulation and it gives you a 9.32. So I turn off my simulation and then I type in for right here 9.32. Okay, and then VC, the same thing. I'm going to disconnect the high. Going to run my wires from here, from the high, goes all the way to the point C. Turn on my simulation and collect my data. So my data there saying it's 6.81. Okay. And now they want to VR1. So VR1, so R1 is right here. So I disconnect this wire here. Disconnect here, run my high to point B. So R1 exists between B and C. So therefore my other side of my connection should be to point C. Okay, turn on my simulation. And that's my value for point VR2. So VR1, VR1. So that's VR1, 2.5. 0 or 2.51, it's up to you. So next thing, you measure current. So turn off that. So current doesn't matter where you measure current. Look like it exists everywhere on this one. I'm going to break it right here. Measure current, put the high side on the tip here, and then the low side on point B. And then switch the mode here to, I need the DCI. So therefore I have to put a shift DCV to go to current. Okay, now that is in current mode, I can run the simulation and collect the data. So that's the value. Collect that data, put it here, 2.52. Okay, so that's the first for the first schematic. So the next one, open. The next one is the number 2. Okay, so pretty much what we did, just similar to what we just did a minute ago. So till this is number 2 would be this one right down here. So 15 volt, look like everything is look like according to the schematic. Okay, so VB is right here. So this, the high side connected to point B. And since it's only point B is only 1 point, so therefore the other side has to be connected to common, reference to the common. Turn on the simulation. So I need to DC. Okay, so turn off the simulation. That is 6.37. And then disconnect this, connect to point C. And on simulation, collect your data. Okay, this is 738.993 millivolt. So I have to convert this to volt. So I take this number divided by 1,000. So this is going to be 0.738. Okay, delete that. Next thing I want to do, VR1. VR1 is right here. So VR1 exists between point A and point B. So therefore, I can put 1 point at point A, and the other side is going to be connected to point B. Turn on your simulation. So turn off your simulation. So the answer here is 8.62. Turn off, and to turn that one off. Okay, next one, VR3. VR3 exists between point B and point C. So therefore, my high side had to be point B. My low side had to be at point C. turn on simulation. Okay, number is 5.63, turn it off. So 5.63. Now IR1, so therefore disconnect this. IR1, so R1 is right here. I can measure before or I can measure after, doesn't matter. So I disconnect there and I'm going to put my high side, the current, the I, so that's represent I. And then that's going to be onto the other side where you disconnect. Okay, now we have to do to change the mode, shift, DCV to change it to mode to current. Turn on your simulation. Okay, turn off simulation. This is 39.19 millivolt. So 39.19 millivolt. IR2, same thing. So disconnect this one, reconnect this one. So IR2 is going down this way. So I can disconnect right here or I can disconnect right here. I usually prefer right on top. So let me see. So current, this one is going to be at point B. And this is at the lead of R2. Turn on simulation. Select your data. So this one come in 13.56. You can put all the value, that's fine. You don't have to put all the value. 2 decimal places good enough. So reconnect that. Next thing, IR3. IR3 is right here. So this one is going to be point B. This one is going to go through point at the lead of R3. Turn on simulation. Collect your data. So the data there is 25.62. And power at PR3. Oh, so this one is just doing the calculation. Okay, so calculation, they should take I squared times R2. Okay, so I square. So I square. So we're going to be taking I square. So this one right here, we're going to square it and divide it by your times the resistance. Okay, so if you look, so first thing we want to do is convert this on into, so you convert this one here first to amp and then potential convert it back to into your original. Okay, so this is going to be equal to, it's going to be, I'm going to open up parentheses. This one is going to be divided by 1000 to get it into amp, and that is going to be square, and then it's going to be times the resistance of R2. R2 is 470. Okay, and then I have to convert that back to milliwatt. So take this here. So I'm going to times 1000 to change it back to milliwatt. Okay, and then this one, the same thing. We're going to, or we can be, let me see if we can take this number exactly here, square it, and then times R3. R3 is 220 ohm. Okay, so that number is way off. Okay, so delete. We're going to do the same thing. Open up parentheses. We're going to be IR3 divided by 1000. That quantity square times the resistance of R3, 220 ohm. And that is there. Now we have to convert that, oops. And we have to convert that back to milliwatts, so times 1000. Okay. As you can see, if you do the calculation, everything's correct. The status should change from fail to pass. Okay. So that's assignment 6. Do you still have any question, Justin? Justin, are you still there?
Yeah, I'm here. Sorry. Yeah, no, that answered my question. I had fundamental error calculating the final power. I actually did the total resistance, not just the resistance of the one resistor.
Yeah, so this one just the resistor. Number 2, we have to do. The first thing we want to do is first thing we always have to convert that. First thing we want to convert the IR2 to IR2 to amp first. So therefore it's going to be, so moving 3 decimal places to the left. So that's 0.01356 amp. And then you got R2 is equal to 470 ohms. And then we can do our calculation. PR2 is equal to this is going to be square and times this value. And then we have to do it just divided by 1000 to convert it to milliwatt. Okay.
Perfect. Yep. Got it.
Okay. And then same thing with IR3. You're doing the same thing. Take this one, convert it first to amp, and do your calculation, and then convert it back to milliwatt, according to what they need here. Okay.
Perfect.
All right. So that's number 6. That's number 6. Let me go ahead and close this. Don't save. Okay. So next thing we want to do is look at the assignment 7. Okay, so enable editing. This one here. So, okay, so 7 we're going to be doing. Okay, so open assignment 7. Assignment 7. So this one's with diode and with all that. Okay, so let me zoom in that in just a little bit. Turn that on. Okay, so change to DC because we're going to be working DC. So this is 30 volt, positive on top, negative. So positive on top, negative on the bottom. Okay, 30, 1K, 1.5K, 4.7K, 4.7K, and 1K. Oh, okay, so 4.7. Okay, so VB. So VB is right on top. So therefore, we're going to look at the voltage at point B. So point B is here. And since this is only referring to a single point, with the other point, that other connection have to be connected toward the common. So common here, you can use common here or common here. It doesn't matter which one it is, just use one. Okay, turn on your simulation, like your data. So that comes to 23.88. And then VC, the same thing, disconnect that, connect it to point C. Turn on your simulation, like your data. Okay, so this is 14.71. Turn off your, so turn it off, disconnect. Next thing, VAB. So VAB, so VA would be at point A, and then the low side would be at the point B. So that's same thing as VR1. So therefore, that seems similar to VR1. So we can turn on the simulation. That's come to 6.11. Okay, and then VBC. Okay, so between point B and point C. So disconnect that. We connect to the high side to point B, low side to point C. Turn on simulation. Collect your data. Okay, so this one is going to be 9.17. So next thing they want to look at VC. Okay, so VC. So we're going to be, okay, so VC is going to be 1 point at C, and then the other point would be at common. Turn your simulation on. Okay, so 14.71, 14.71. Okay, V out. So therefore we're going to put V out. So V out is going to be over here. Okay, so V out. Since V out is only at 1 point, so therefore the other had to be connected to common. Turn on your simulation. Okay, turn off your simulation. This is 683.383 millivolt, and we have to get to a volt. So therefore we're going to take this number divided by 1000. So therefore it's going to be 0.683 volt. Okay, and then I through the 1.5. Okay, so let me disconnect this one, change the mode, shift to current, and then we're going to be the 1.5K. So I can disconnect before, or I can disconnect it after. So I'm going to take it after. So the high side is going to be at the lead of LR2, and this is connected to the and the low connected to point C. Turn on your simulation, like your data. Okay, so that's yielding 6.11 milliamp. Okay, so 6.11 milliamps. So VR4, so in this case, we don't have to do any calculation. We just measure. Okay, so reconnect that one again. Okay, VR4 is between C and out. So therefore, this one had to be the high side at C. The low side is going to be at the out, V out. Okay, so turn on and change it to voltage because that's what we want, volt. So back to DC volt. And turn on your simulation, collect your data. Okay, so that's giving you about 14 volt, 14.02. And so if once you get collected, that all should get you to the passing. Okay. So do you have any question on number assignment 7?
No, thank you. That's
Okay.
perfect.
All right.
Sorry, can I ask a couple of questions?
Yeah, go ahead.
I noticed that for 2 or 3 of the different measurements, when you didn't round up, even though the next digit was a 5, and I know that you typically round up, but you don't round up. Is that why is that?
No, because I know the instructor said about 5% error. So therefore I can put exact value, or I can just use 2 decimal places and just truncate the rest, or I can round it up. Doesn't matter which way it is. Depending on which company that you work for. So whoever's you're working for, they will tell you whether they prefer something rounding up or just drop whatever additional value, or just give me the exact value as you see on the meter.
Got it. Just another question. The diagram in the Excel, I noticed that the resistors aren't labeled. So you might want to label them.
Well, you don't need to know. You don't need to necessarily know the label.
No, but you do, because you're in one instance you're asking for power in R4. When I looked at the diagram, I didn't know which one was R4.
Yeah, VR4 right here. So yeah, that's the only thing that it doesn't show you. But yeah, usually we go from left to right, and so yeah, this one.
No, I understand. But again, just for clarity, I would advise that you just add that label in.
Okay, well, that's the instructor's when he's assigning the homework, and so I don't have any control over that. Okay, I only just show you how to work it and collect your data.
Thank you.
You're welcome. Thank you. Okay, any other question?
Yes, Sam, I got a question. Is
Okay.
there a difference when you go to I or then you go to H or high? I'm sorry.
What do you high and low, or you stay on the oscilloscope on this meter, right?
Yes. So is it a difference when you go to the high or the red, or they go to the one where the I is at all the way at the bottom? Is there a difference to
I
it?
is for current, right? I is represent current. High
Yes.
here is represent either voltage, ohm, or the diode.
Oh, I didn't see
They
that.
label, yeah, they label right there, right on top, and you can see the symbol. They label, everything has its label. So I's always represent current. If we need to measure current, I need this connection. So if I look at this one here, so this represent this point, this one represent this point, this represent this point, this represent this point, this represent this point. So therefore, if I need to measure current, I have to break my circuit first and take that, connected my current to wherever the starting lead, and then my low side is going to be connected to the other side where the break occur. Okay, and then I change my mode here from shift, change this one to go to the top point, which is a DCI for current. Okay, so once you have that set up, now you can turn on your simulation and collect your data, and then turn it off. Once you have a reading, you can go ahead and turn off your simulation. And then once that you got your data, just collect it here and then just put it on the Excel. Whoever it is, whoever you're going to collect this data for, they're always going to put whatever they needed. So you collect the data for them, and if something that they said is wrong, then you have to go and retest it for them. Okay.
Okay, got it. Yeah, because I didn't understand it, so I started using the The one at the very top one.
Yeah, that's why that's why we said, always goes into here, because we did, Mr. Tai did go through go through how to explain the use, how right here, said run MSIM7 on assignment 4. See, if you watch this, he went through and he explained it, which one that you use in detail.
Okay, I'll watch
Okay.
it.
So everything is always listed, and just the video is always going to be helpful. Okay, any other question on the assignment 6 or 7?
Hey, Sam, just a basic question. I pretty much think I got my own answer, but the red button on the left and the black button below it on the left, go over, yeah, right there, those two. Pretty much we're not using those too much, huh?
If we're going to look at something in the high rating, in the higher rating, yes, we will use it.
I'm
But
not
we're
saying
not
we
using-
don't, but I'm
not-
saying pretty much we haven't been using it too much.
If we don't teach you, don't use it. Okay, just use the one that we just showing you.
Those,
Everything
those,
else,
those three buttons on the right, we use those more than anything.
that's it.
Yeah. Thank you.
Just follow the example that we show you. Just do that. That's all you have to do. Just if you can copy what we do, then you'll be fine. Don't try to do anything else.
Thank you.
Just learn that. Yeah, just learn that minimum amount. You're gonna be fine. Okay.
Thank you.
All right. You're welcome.
A stupid question. Where's the simulator?
The simulator. What do you mean the simulator? Like
do I
on the
find
MSIM?
Yeah.
MSIM that you should be downloaded on your computer.
Is he talking about the button up to the left where you click on all the time?
Oh, the switch turn on and turn off, which is for me, I moved it here. Before it can be exist all the way on top here somewhere, and so you have to do it, just put wherever is convenient for you.
No, but I mean, was he referring to the fact that he was calling it, you were calling it a simulator? I'm not really questioning it. I'm just saying, is that what he was referring to?
Okay, well, Joseph, let him speak, please.
Okay.
Okay, go ahead. What's your were you referring to?
Just this program. Yeah, you said download it. So where's the link?
That link should be on the website. Mr. Tai did went over that. See right here, is it download and run MSIM. So you watch this video, he'll teach you
Video.
how to do it. And that handout is under handout, and it should be in the bottom. It should be saying, scroll down, and it's a MSIM7 right here. But if you watch the video, Mr. Tai, watch the video, and he'll walk you through step by step. Okay, so the video, it's right here. So just click on this one. It will open up a YouTube, and then you just have to do just watch and follow his instruction. And then you can stop and you can speed it up, and so that way you can, if you need it, go by step. See? Okay, so yeah, just go watch that. And the handout is, the MSIM is under handout menu, and then it's MSIM7 down here. And so you're going to need to download this one to MSIM7 student version.zip. Okay. You got that, Luke?
Yeah.
Okay. All right. Any further question on any assignment or anything? Okay, back to you, Mr. Pham. Thank you.
Thank you, Sam.
You're welcome.
OK， 你要带什么东西啊？这个。
Okay, let me get it back to my iPad.
Let's go.
Okay, last time we already talking about the diode. And also zener diode. Try to understand, really understand, okay, how to solving the problem with either one. Okay, now I want to asking you. Okay, for this circuitry, we want to know the zener. They can be breakdown. They can be on normal. They can be open. And also we want to know what VO equal. Okay, who now telling me? It's supposed to be answered quickly.
Out 5 volts.
But after telling me, zener breakdown, are they just on normal? Are they be open?
Breakdown.
Which one?
Breakdown.
You said they will be breakdown.
Yes, sir. So B out. So B out will be 3 volts.
Okay, either they can be breakdown on normal or open, telling me which one.
Uh, Breakdown.
Breakdown.
Yes, sir. Because there's gonna be 5 volts supplying the in the reverse. 5 volts in the reverse, so the output will be 3 volts.
Okay, any objection, anything, or you don't know?
Because we have a voltage divider here. So we divided the voltage and supplied 5 volts to the zener diode.
Exactly. First thing, in order to solving the problem with the diode, the zener diode, and you're supposed to be, if no zener, what the voltage at the Vout. This is just a voltage divider. 10 times 1K divide 1K plus 1K. So basically, voltage divider given you 5 volt. And the 5 volt greater than 3 volt zener. So zener will be breakdown. And Vout will be equal 3 volt. Is correct?
Yes, sir.
Okay. Now I can this one. Till 1K. Okay. However, 10 to minus 10 volt. Same thing. What happened to the zener?
It will act like a normal diode.
Okay, for minus 10 volt. So if you without the zener and you know to calculate, you get minus 5 volt. That means at this point right here, minus 5 volt.
Mr. Fairman,
This side will be 0 volt. So diode will be working normal.
and Mr. Pham, is that because you have 0 volts minus a minus 5?
You mean you take minus 10
Right,
times
right,
1K.
right.
That's why you get minus 5 volt.
Right.
If you get a minus 5 volt, then this side 0 volt, diode will be just working normal.
Right.
What Vout equal?
0.7.
Negative 0.7.
Okay, and you understand when the diode on normal, then you substitute diode by the battery. This side negative, this side positive, minus 0.7
Yeah.
volt. Okay, any question? Anything? Okay, if it's not, let's see. Where we go last time. Now, go to this point. So now they will be using AC. They apply sideways. Okay, V in 5 volt, and the other side will be 5 volt. So basically, V peak to peak equal 10 volt. Okay. So normally, if you don't have a zener diode, and the input output will be the same. Okay. So, however, when you get a zener diode, for positive, you get 5 volt. Okay. And a 5 volt will be higher than zener 3 volt. So zener will be breakdown. Okay. So that's why you get 3 volt. When you get a negative here, okay, so you get a minus 5 volt maximum. Okay. Then you get a route on the other side. Zener will be working normal. Okay. And they working normal. That means on this side will be positive, on this side will be negative, and the value will be 0.7 for the silicon. So that's why you get -7 right here. Okay. So this is normal. Okay, any question on that circuit? If you run the simulation with the MSIM7, you can see they will be the same exactly. Only the value, maybe not minus 0.7. They can be minus 0.6 or minus 0.65. Okay, that doesn't matter. On the next circuitry, they just reverse the zener diode. And now you can see they can work in opposite to the one on the top. Okay, anything. When you're working really on the left, they will be same thing. Okay, so now you can see same circuitry. Only thing is they're using two zener. So when they're using a true zener, then you can see in the at the positive peak voltage. Okay. Then one zener will be breakdown. Okay. So for this one here, okay, let's see. Which one will be breakdown when you get positive? D1 or D2?
D2.
That means for this part right here. D1 or D2 breakdown.
D2.
That means you can get 5 volt right here. That's a peak voltage. Which one breakdown? D1 or D2?
D2.
Correct. D2 breakdown. D1 will be. But D1,
Normal. Normal operation.
normally, okay, D1 normal, this side will be positive. This side will be negative, 0.7. So that's why you can see they can telling you for the positive part, the output will be equal plus VG1 adding to 0.7. I think that you get one positive negative for 0.7. And for the negative, they just opposite. Okay? For the negative, then D1 will be breakdown. And D2 just on normal. D2 on normal, and you can get positive on this side here, negative on the other side, and the value will be 0.7. So that's why you can see I can get this negative voltage here minus to 0.7. Okay. Another circuitry, almost the same thing. However, the output input will be 10 volt. Okay. And you can see for this part right here. And we already know the breakdown will be 5.1. And adding to 0.7, you get 5.8. Okay. And for the negative, okay, then the one right here will be breakdown, 3.3. Okay. And also you can get this guy will be on normal. So that's why 3.3 adding 0.7, you can get minus 4 volt.
Hey, Mr. Pham, can you write that on there for us?
What?
Can you write that on the
Okay, so that one here, okay, I can say it right here. D1. D2. D2. Breakdown. D1. Up. On the other side, D1 on, D1 breakdown. D2 off. Normally, try to learn and get along with the multi-sim 7 simulation. If you know how to using that simulation, that will be helping you to solving any problem. Okay, and also that will be helping you when you do the lab in the lab. Okay, supposed to be no problem. You get your program. One will be MSIM7 simulation, and another one will be PSPI simulation. Now, try to see what the difference. MSIM7, that means try to helping you understand how to using the test equipment, either DMM, oscilloscope, to do the job. Exactly when you're working on the real circuitry with the real equipment. PSPI, that's more theory, okay? They're not really exactly what will be going on when you're working in the real circuitry. So depending on application, sometimes we need to using PSPI. Sometimes we can using MultiSim7. Okay.
Mr. Pham, so when we're doing these problems like this, if we run into a problem, it's best to use the MultiSim7, correct?
Yeah, that normally you can use in MultiSim7.
Okay. Thank you.
So that's why when you run the simulation, I already telling you using what? PSPI or MSIM7. Okay. At the beginning, on the time, you will be using MSIM7. However, on touch two, they will be using PSPI. The thing is that deal much theory, like the waveform, okay? Not like sideways. And also this problem, the same thing, like we already did. Only thing is, you try your best to see you can get 6.9 or minus 15.7 volt. Okay, line emitting diode, LED. This is easy. You can see LED. Okay, when they on, you can see the light turn on, turn red. Okay, and this is just the physical. That's the real one. Okay, when you're working in the lab. And now this will be show you the 7 segment. Try to communicate with the human. That means when the computer send out number 9, decimal, you know number 9. However, computer will be 1001. And human cannot understand 1001. So they need to go to the segment and they display for you number 9. That's what they call a 7 segment. See how many segments? 1, 2, 3, 4, 5, 6, 7. Each segment just one diode. Okay, you can see that just a one diode. Like number 9, they turn diode A on, B on, C on, F on, and Z on. So that's why you can see number 9. They're using everywhere. Okay, they must get the 7 segment in your watch. Okay, if they're using digital, then they must be using 7 segment. Next one, rectify, halfway rectify. Now, what the rectify circuitry will be doing?
It's gonna be converting alternating current to direct current.
Can you say again?
AC to DC, alternating current.
Exactly. That is exactly. Rectification, I already said. Rectification means converting AC to DC. Now, you get an outlet in your house. This is a sideways. 110 volt. What that voltage here telling me?
RMS.
RMS. Okay. The thing is, this a sideways, you can get a V peak, you can get a V peak to peak, or you can get a VRMS. Okay. 110 volt in here. That means RMS voltage. And that's a AC. That means positive current going one way, negative current going different way. That's what they call AC. When they go into the rectifier, and now you can see the signal only positive or 0. That means the current flowing only one way. Okay, if you get a current. So that's why they call it DC. However, that they call it post DC. Okay. Now, we'll see this one. So
Sorry.
basically, you can get AC, go to the rectifier, and this will be AC right here. So we already saw the signal at this point, they will be go this way. Okay, that means the post DC. Now, they go to the filter. Okay, that means in the filter here, what's supposed to be inside the filter? Who knows?
Capacitor?
Exactly. Inside here, you get the capacitor. Okay. Now, by the way, we're talking about capacitor. So basically, capacitor will be charging, keep the voltage. Okay. They can be charging up to maximum how many volt. So, in general, capacitor will be get what they call IC. capacity reactant equal 1 over 2 pi F C. Okay. IC unit will be in ohm. That will be telling you capacitor, they can get a resistance. However, they're not called a resistor. They call a capacity reactant. And they will be calculated by formula 1 over 2 pi FC. Okay? In this formula, two pi, you know pi, 3.142. F have to be in hertz. And C must be in farad. That's a unit of the capacitor. And now, capacitor have to deal with either DC or AC. So if I said for AC, what IC equal? For DC, telling me what IC equal. Yeah, you guys have to working with me, okay? Either you can get it right or you can get it wrong. But I try to help you to understand.
What was the question?
I said for the DCs, what the IC, that means capacity reactant equal.
1 over 0. There's no frequency. 1 over 0.
Equal what?
Infinity.
Okay, you're good. Now, for the DC, and you understand the F will be 0 hertz, right?
Yes, sir.
DC have a no frequency. So IC will be equal 1 over 2 pi times 0 times C and 1 over 0 equal infinity O. Okay? So that's what we said. For DC capacitor open. That's only telling you capacitor not allow DC current go through it when they get the full charge. When they full charging, then they open. DC current cannot flow it. That's what we're talking about. For DC capacitor, they could be open. Okay? And now for AC. What frequency equal?
60 hertz.
Equal what?
The given 60 hertz.
Yeah, you can say 60 hertz, 1 kilohertz, 10 kilohertz, or whatever number. Okay, however, I say F equal infinity. So no one can say any number bigger than that. And now you can calculate HC. 1 over 2 pi FC equal whatever time infinity. And that will be telling you 0, 0 ohm. 0 ohm means the capacitor will be shorted for AC, just like the wire. So we can say capacitor shorted for AC. That's only telling you capacitor, they allow AC signal go through it, but not the DC. That is a very, very important for everyone learning about electronics. Okay? Any question about the capacitor? Make sure you have to memorize. For the DC, capacitor will be open.
I have a technical question, Mr. Friend. I was wondering if you can kind of answer it, though it might be kind of difficult, maybe more of a puzzle. That's why I asked the question. So if a capacitor has current flowing through it, what is the difference between DC current and AC current? If AC can flow through a capacitor, but DC can't.
DC current cannot flow through it if the capacitor already get the full charge.
Current is current, correct? Neither positive nor negative? Or they fluctuate in its polarity, correct?
Now the thing is, you know, if you're talking about DC, current only one way. Current cannot be negative. If you're talking about AC, okay, current can be go to the left to the right or right to the left, depending on input positive, negative.
So is DC current technically part of an AC current until it stops going one direction before it reverses and comes back?
What do you mean reversing?
Well, both signals are traveling in one direction, but only one of them stops and then the other one reverses and comes back. That's AC. AC goes forward and then comes back. DC just goes forward. Right.
Okay, if you're using, if you're talking about DC, no matter which way, capacitor have to be open. AC capacitor will be, you get sideways in, they give you sideways out. That means they allow the AC current flowing. Okay, and now when you're looking at the output of the filter here, you see look like that one. And then go to the filter, okay? And basically the capacitor will be charging up. That means they will be 0 here. They can charging up to the point right here. They're telling you right here that the DC voltage. However, on the top of that DC, this signal here, well, now what is it?
A ripple.
You see that? They draw for you, given to you at this point. And I telling you from 0 up to here, okay? That may be that DC voltage. However, on the top, you can see they look like that one here. This signal, what is the name of this signal?
It's still AC current, isn't it?
I want to know is the name of that signal.
Is it a pulse?
What?
Pulse?
No.
Pulse. DC.
Pause. No. You have to telling me. That one, the guy will be see it on the top. That means on the top of the DC, you still get some signal.
You mean
It's the
ripple?
top one.
Exactly.
You mean ripple?
Exactly. That we call a ripple. The name is ripple.
The AC.
Okay. Now,
Hey, Mr.
Okay.
Sam, one thing, ripple is what AC riding on DC?
they must be on top of the DC.
Okay, it's AC riding on DC.
Right. However, what is the ripple? What is it?
Noise.
Exactly. That basically just the noise.
Does it have the potential to charge a capacitor?
Exactly. Depending on the capacitor side, depending on the frequency.
But then for DC, it's only charging half of the capacitor since it AC has to reverse back on itself. Is DC technically only charging one side of the capacitor?
Yeah, they can be charging. You can see they draw that one. Let's see. Okay. They can draw that one here. That means they charging up, they discharge. Okay. That means they charging up here and now they discharge it. So that's why on the top they still get some signal we call a ripple. That will be a noise. Okay. The thing is, if you get a 5 volt, you want the 5 volt just straight at it. No signal on the top, no noise. That noise can cause for the part on the circuitry, they're not working. Like when you're working on a digital circuitry, you can see you take the input, everything good. However, output not coming like you wanted. And that will be telling you, you get a noise.
Well, here's a technical question. I mean, I know that we're clarifying the DC AC. So the ripple technically is charging the capacitor, but it's not continuing all the way through like an AC signal. It cannot complete its cycle. It cannot pass continuously through the capacitor. So it's being blocked. That's what the capacitor is used for. It's a block. So if one side of it is charging, why is there a high amplitude and then a lower peak, what looks like a lower discharge peak of the DC signal? Because you have, right? So what I'm basically saying is, so how is it able to discharge? Is it discharging on the reverse?
What do you mean reverse?
The reverse of an AC signal, or is there a slow drain?
Another thing I did is the sideway will be look like that guy here.
Right, but then that discharge, I mean, because that lowest peak on the right-hand side of where your arrow is.
Okay, this is a discharge, right?
Well, yeah, either on the where you just mark the arrow or in the circle where it says DC, where the filtered voltage is. Either way, there's a discharge, right? So what point of a capacitor, where within the capacitor?
No, that is what
is it draining?
designer.
That's what I'm saying. When are you saying a designer capacitor?
Yeah, if you design, then you have to make 5 volt this way. They don't want any more here. They don't want ripple on the top.
The ideal for the signal filtration, possibly.
Yet cannot be any ripple or very, very small ripple.
Right. So I'm just trying to clarify if a DC is fairly stable in its charge line, right? I mean, there's not much of a negative pulse in it, right? I mean, either because there is no real negative in DC, but the peak value is technically showing almost a negative because it's decreasing. So how does there, within the example, have a high peak and then a low peak? What is considered to be the actual location for a discharge for a DC voltage or current?
Okay, if you want, you can run the simulation. Okay. In order to make sure you can try to get straight DC voltage as much as you can. Okay, you can change the size of the capacitor, and you have to change the signal charging. That means the frequency will be high. Okay, so they track and they try to discharge, and they already just keep going. That will be giving you the straight DC voltage.
Right, I understand, because that's cleaning the frequency signal to have less noise. So the faster that it charges and discharges, you have less ripple. So the straighter the line, the cleaner your signal, or the cleaner your whatever you say, whatever you're trying to listen to, there's less noise. You're trying to improve the signal clarity, but with a quick discharge and a quick charge using the calculation like you're showing.
Yeah.
The capacitor and the frequency are both relative in order to have a clean signal. I understand. Thank you.
That's why we working, myself also, working with the government. When we design the circuitry, they can asking you, they want 5-volt power supply. Okay, and also they asking for the ripple have to be plus or minus how many percent. That means you must be designed so they can meet the requirement. Okay.
I'm sorry.
Now, I expect you to know on that one here, try to remember XC. XC we call a capacity reactant, and they calculate by formula 1/2 pi FC. In this formula, XC will be ohm, F will be hertz, C will be farad, pi will be 3.142. Okay, that is the formula. And then have to memorize for the DC. Capacitor will be open. That means they not allow any DC current go through the capacitor. For the AC, capacitor will be shorted. That only telling you capacitor will be allowed AC signal go through. Okay. You can see, and then on this picture here, they can go to a next one will be regulator before they go to the load. And on the regulator, they don't want any more ripple. You can see that on this one, you get a ripple. However, after the regulator, you don't have any more ripple. Okay, and on the next, you can see what inside equal. Now, when you see this circuitry here, very simple. This is the load. Input will be AC right here. Okay. And output, when you get input positive, diode will be on. So they allow this signal go to the output. When you get a negative signal, diode will be open. So that's why output will be 0. And they keep repeating. Now, this signal we call a halfway rectifier. Why halfway? That only telling you. Halfway means they just allow only positive to go to the output, but not negative. That will be halfway. Okay? And in this output here, frequency output and the frequency input will be the same. Okay? Now, on this drawing here, they said we get the diode will be ideal. What that mean? VD equals 0. So that's why you see 0 here. Okay. However, normally it's practical. Okay, in practical, we have to using 0.7 volt for the zener, for the diode. Okay, so really, if you draw for the practical diode, then signal will be go this way. Okay, they will be go that way. And the value right here, minus 0.7 volt. Okay.
Mr. Pham,
Yeah.
so if you looked at, I think you're leading to this, maybe I jumped in too soon, where it says V out equal VN at the bottom, and then it says second approximation, VP out is equal to VPN minus 0.7. So depending on how many diodes you have, you're always, say if you got one diode, it's minus 0.7. If you got two diodes, then it's it's minus 1.4 or something like that.
Yeah, will be. But right now, we're on halfway.
Okay, you're only dealing with one diode, okay.
Yeah. So the thing is why they say VP out equal VP in minus 0.7. The thing is you understand the VP will be measured from 0. That will be VP. Right?
Right.
Now, this signal will be going down to 0.7 volt here. So when you measure VP, you measure from here to here. So that's why you need minus 0.7. They're not the same like the 0 volt for ideal. So when you run for the simulation, you can see exactly. VP will be measured from 0 to the top. However, the signal going down 0.7 volt. So they VP now they will be from here to the peak. Okay. So
and the frequency for the input and output for half-wave rectifier is the same.
Exactly.
Okay.
Okay, so what I expect you, when you see this circuitry, you have to understand this is a half-wave rectifier. They can rectify only a halfway of the input signal. Either you can see diode, they connect here, or later on, they can connect here.
Question, Mr. Van?
That means one half rectify positive, another one rectify negative. Okay, you get a question?
Yes, can a diode like you're showing right now, can it help speed up the charge time of a capacitor if it's in the circuit a specific way? So that the peak itself doesn't have to travel so far before it completes its cycle? Can it help actually speed the charge up somehow?
Yeah, that's what you're talking about, the dribble.
Right. So I'm just, why I asked that is I'm also applying the same thought to your example of the Butterworth and the Bessel signals as to what's the best signal source to work with in receiving the best frequency channel, whatever channel you're trying to listen to on the radio. There's you have the
Okay, the thing is, you get the capacitor, they try to get the DC output. And sometimes you can get the ripple, the noise on the top of the DC. So what you try to exercise, that means make the ripple small as possible. Okay, you make a small ripple, you can change the capacitor, or you can change the input signal frequency. Okay, you can easily to exercise with the MSIM7, and you can see that. Okay, the thing is, this is not a hard part. Just we need to accept it. Next one, transformer. What we're using the transformer for?
Step the voltage up or down.
Now,
To convert it.
Step down voltage, step up voltage.
To convert it from a 120 to 24 volts.
yeah, but that is a specific value. But general, what transformer doing? I just asking about general for definition.
Transfer other to other.
Okay. Basically, transformer will be transfer the signal from one voltage to the other voltage. Okay. You can see you can get the transformer everywhere. They converted, okay, from 120 volt to 12 volt or whatever. Now, they said transform one voltage to the other. Okay, remember that. Not a AC to DC. Okay, no. They just transform one voltage to the other. The first one here, they call a primary VP. And the secondary voltage, that will be VS. Okay, and also you can get a NP and S. That means the winding for the first part here and the winding for the second one. NP number of turn in primary and that will be number of turn in secondary. And you get the formula NP over NS equal VP over VS. So that will be telling you, you can calculate the secondary voltage equal NS times NP, VP, divide to NP. Okay, if NS, that means the secondary winding greater than the primary winding. Okay, transformer will be step up. That means you apply 120 volt here, they can coming out 240 volt. Okay, step up and step down. Depend on NS greater than or less than NP. Okay, NS less than NP, you get a step down. You get 110 volt here, you can get 24 volt on this side. That's nothing else. Okay, very simple. Now, I quickly go to this one. Okay, make sure you need the time to go over. Okay, make sure you understand. Still halfway rectified. However, in this halfway rectified, they're using transformer. This is a transformer. Okay, 2 to 1. So basically, you can see NP equal 2. Okay, and S equal 1. So 156 volt peak here. So you need to know what the voltage on the secondary. That means you need the VS right here. You get the VP here. Okay, you're using the formula. Okay, VS equal NS times VP divide NP. Okay, let's see, NP here. and F. Okay. So you need to calculate the V. Let's see, peak voltage, secondary voltage. The peak secondary voltage.
Is
Okay.
that 2 times 156?
That's the VP.
Right, right. It says, letter A says the peak secondary voltage, V peak secondary. And it's a step up by 2 to 1. So you'd multiply 2 times 156, correct?
You apply the formula. Quickly telling me, you get the V primary 156. What the V secondary? See the formula. V secondary equal NS over NP. V secondary NS over NP times V primary.
$78.
You take the 156 divided by 2, right?
Yes, sir. 78 volts.
Okay. The rectified peak output, we pick out.
Oh, yeah,
That
yeah,
means
yeah, yeah.
we pick out here.
That's 1, that's 2, that's a half, 0.5 times. Oh, yeah, I was wrong on that. Yeah, it's a half times 156, so you chop it in half.
Okay, now,
Hey, Mr. Pham, a question. When it says 2 to 1 like that, is that step down or step up?
step down.
Step down, okay.
You can see right here, right?
Yeah, okay. That's right. That's why you cut it in half.
Now, you can see the signal at the output here, how they look like. This is 0 right here. So this is the circuitry halfway rectified. Only they using transformer to get the AC. So when input is positive here, then the output, they will be positive. Okay. However, they will be go look like. Right? What the value here?
Is that because of 0.7?
Minus.
0.7.
The thing is, when positive, the diode will be on. Diode will be on. You must be substitute the diode by the battery. Positive on this side, negative on this side, and 0.7. So that's why you're going down minus 0.7.
So the answer on the output, Mr. Pham, would that be 78 minus 0.7?
Exactly.
Okay.
Mr. Pham.
Yeah.
NP and NS, the yellow rectangle, that's technically a magnetic field, correct? Those coils aren't touching, right? It's a magnetic field.
Right. They're turning around.
Right. So no wires are actually touching. That's a magnetic field influencing the coils.
Right. If you go detail on the transformer, okay? But the thing is, we not go to magnetic field.
Right. I just interpretation of the schematic.
Okay. Number C, frequency input 1K, output will be 1K.
Hey, Mr. Pham, so the output voltage was 77.3 then? Because it's 78 minus the 0.7. So letter B should be what, like 77.3. Did anybody else get anything different?
You guys try to understand. I run this program exactly the same like we in the class. However, at the Zoom, you can learn more. Okay? So that's why you need to follow it. Try to work with me. Okay? In order, don't waste your time. Don't waste my time. I want you guys to be a good technician or engineering if you keep going. Okay? Not much time. However, you have to go through over. When you see the circuitry, you know right away what to do, how to do, you'll be okay.
Mr. Pham,
Yeah.
the schematic there, it shows two coils, the left side and the right side. Two is a coil and one is a coil. Now, a transducer is technically a coil, correct?
Yeah.
So is a transformer technically is the transformer technically two transducers? Just with different wraps of coil or wraps of copper? Is that technically what a transformer is actually two transducers?
No, the thing is, if you want to know more detail, then you have to get the textbook. Okay, or you can go to Google. They can explain detail on the transformer. However, we just a technician. We want to deal with the input and the output. We not try to fix the transformer. Okay?
Hey, Mr. Pham, if I could just ask one question.
Yeah.
For the purpose of the recording tape, can you write down the answers A, B, and C so when we see it on the recording? A is 78, B is 77.3.
Okay. Big secondary here. What you get?
You got a 78, I believe it was.
Bring what?
No, just 78. And then the rectified output is 77.3. 77.3.
78 minus
0.7. And that's 77.3. And then the frequency for the last one is the same.
Yeah.
It's just, I just want to make sure we get that on there. So like when we look at the audio tape and you're not around, we can have this for an example.
Okay. Okay, any question to me?
Before you end the class, yeah, I have a technical question. Maybe you can answer it the next session. I'll remind you. It's just a technical question, so I'll ask it anyways, Mr. Brown. If a transducer or the transformer on one side, only one coil, can produce a magnetic field, and that
you're talking about the transistor?
Just transformer. So if a transformer, one side of it produces a magnetic field, right? And then compare that to just a coil, which would be, as an example, a transducer, right? Both have the ability to produce a magnetic field, all right? So if I take a transducer and I put it close to a capacitor and I run DC signal, a DC current voltage into the capacitor, I know that capacitor is going to block the DC. But if I also use that transducer to influence the magnetic field around the capacitor, would the current from one side of the DC of the capacitor actually jump across to the other side of the capacitor by force, by the actual field, the magnetic field that the transducer produces? Can a transducer actually cause that current to flow from one side to the other? Is that possible? And I know the simulation might be difficult to prove. And yeah, I would actually have to set up an example. But do you think it would be possible if a transducer could actually influence the DC current to jump from one side of the capacitor to the other so that the current still flows?
Now, if you get the AC, then the capacitor still let it go,
Right. So I'm talking only DC.
but not DC.
You don't think the magnetic field would allow the
No.
current to go? Because all we're doing is charging one side. We're just charging chemicals.
No
Right.
matter what, if they charging, they via AC, then they can pump capacitor.
Right, I understand. So it's staying.
But the DC, no. Absolutely. Okay, so you get any question to me? Okay, for any student, you start before 2020. You need to email your name and your ID to me. I take it out. We try to get the certificate for you guys. Okay? Start at the 2020. Nobody can get certificate at the time. The reason is we done for too many times of the lecture. However, the labs we stop. Okay. I hope this week, after this week, we're able to return into the in-class lab. I'm asking for a little more time, so at least I can open 4 days a week or 5 days a week for the in-class lab. We will help your guys to get as much at the lab done. Okay? For next week, for this week, we can get a long weekend. We don't have a class on Friday, holiday. And also we don't have a class on next Monday, also holiday. Okay, any question to me? If it's not, good night, everyone.
All right, Mr. Pham, thank you.
Thank you. Good night.
Good night.
Good night.
Thank you, Mr. Pham.
Good night.